Good evening, everyone. Today is the 11th week of live session of fluid flow operations. So, in this week, we will be learning mostly about the flow measurements, right? How to calculate the flow velocity, flow rate of a certain fluid kind of thing. So, different flow pressure difference kind of thing. Okay. So, how the flow parameters are measured with different instruments, we will learn this here. Okay, so I'm sharing the screen. I hope my screen is visible. So first we'll first go through the basic flow measurement summary of it, and then we'll go through the lectures, and then we'll go through the questions. We'll solve some problems. Okay. The first is the flow measurement. So in different ways, flow measurements can be done. So first one is the restriction flow meter. Restriction flow meter. Second one, area flow meter. Third one, local velocity measurement. And the fourth one is the open flow measurement. So under restriction flow meter, there are two types of instrument we can use. First one is the orifice meter. We will come to each one of this instrument later in detail. For the time being, remember this is the orifice meter, and second one is the Venturi meter. Okay. In area flow meter, there are many. So some of them can be, first one is the rotameter. Second one is the target meter. Third one is the turbine meter. And there are some many. Okay. In local velocity measurements, there is pitot tube, which is very important. There is one of the example is pitot tube. And in open flow measurements, there are rectangular wares and notches And the second one will be triangular, where are notches. Okay, so these are the basic instruments or equipment you can use to measure the flow parameters. Now we'll see one by one. So in case of restriction flow meter, so first we'll draw a diagram. So what is restriction flow meter? So there is a layer, suppose. Okay. So it means here the flow is happening. Okay. The inlet diameter is, suppose you can call it D1. Okay. And this is the region 1. This is region 2. And here there is a restriction to the flow, this region. Okay. So now the velocity will go like this. It will spread like this, right? If the fluid is coming from here, it will spread like this. And this is the velocity profile of it. Here the velocity is v2, right? And we can think that this area is AT. Okay. And in this position, the pressure is P1, and in this position, the pressure is P2. Okay. So this portion is called the vena contracta. Okay. So what is vena contracta then? If you can remember the definition. So the region where the cross section of the fluid flowing through the channel attains minimum area. Okay, so in this region the minimum area is represented by this portion, so it is called the vena contracta. Now we want to solve it. Like what will be the velocity profile and its equation, right? So we will take first assumptions. So what are the assumptions? First assumption is, obviously it is steady state flow. Okay, that means it is not changing with time. Second one is incompressible flow. That means the density doesn't change much with time and space, right? Third one is the uniform velocity or velocities at section 1 and 2. That means in this section and in this section the velocity is uniform. Okay. Next, the fourth assumption is no curvature of streamline. Fifth one is no curvature of streamlines means that is pressure at section, pressure is also same. Okay. So velocity is also uniform in the section 1 and section 2 as well as pressure. So this means pressure is uniform in section 1 and 2, right? Fifth option is no frictional loss. Okay, so we are here to try to find the basic equation through which we can actually define the system of restriction flow measurements. Okay, restriction flow meter. So here that is why we are taking so many assumptions to simplify the basic equation. And if you can keep adding those things, each assumption, then the equation will be changing with time. Okay. And the sixth assumption is it is in the same plane, horizontal plane. So that means Z1 will be equals to Z2. And the seventh assumption is alpha 1 and alpha 2 is equals to almost 1. So this parameter is used in Bernoulli's equation, right? This is the kinetic parameter, kinetic factors. So now we are writing the continuity equation. So in continuity equation, what is there? So it is not the Navier-Stokes continuity equation we are going to use here. Okay. It is coming from the basic Reynolds transport theorem. If you remember this, so there are three terms, right? First one is the rate of change of extensive property. Second one in the control volume. Second one is the rate of change of intensive property in the control volume, and third one was the net flow. So we are considering the net flow first. So from here, when we are taking that rho, that extensive property to be 1, right? Then comes your mass balance equation, that means the continuity equation. If you remember, if you don't remember, go through the lectures. I have taught these things in, I think, in second lecture or third lecture. Okay, in the YouTube channel. Okay. So from here, net flow rate we want to calculate. So net flow rate is this. Velocity into area is 0, right? So for this two section, for section 1 and section 2, we are going to measure everything. That means, so we always consider going out of the system as the positive sign, right? So that means in case of section 1, the flow is coming inside, right? So here we will be taking a minus for that. So it is minus V1A1 plus V2A2, because from this vena contracta region fluid is going outside, equals to 0, right? That means what is coming? V2 is coming as, sorry, this is A1. V2 is coming as V1 A1 by A2, right? So this is the V1 V2 expression. This is how we can calculate. If you know the diameter of these two inlet and outlet, you can calculate the velocity, flow velocity at this vena contracta region. Okay. Next comes the Bernoulli's equation. What is that? So the general Bernoulli's equation is P1 by rho plus alpha 1 V1 square by 2 plus Z1 is not here. So I am taking equals to P2 by rho plus alpha 2 V2 square by 2. So we already know that alpha 1 and alpha 2 are considered 1. So we are not writing this two. So now P1 minus P2 by rho is equal to V2 square by 2 minus V1 square by 2, right? So now if you take common V2 square by 2, it will be 1 minus V1 square by V2 square, right? And this can be written as V2 square by 2 into 1 minus. So from this ratio, we can write that V1 by V2 equals to what? A2 by A1, right? So it will come as 1 minus A2 by A1 whole square, right? Now what is in left? P1 minus P2 by rho. Right? Now what we can write? So P1 minus P2 can be written as delta P by rho equals to V2 square by 2 into 1 minus A2 by A1 square, right? So now if we want to solve V2, what will come? So V2 will be 1 by root under 1 minus A2 by A1 square into root under 2 delta P by rho. So your delta P is P1 minus P2. Okay. So this is the expression if you know the pressure drop also. Okay. Pressure drop of the fluid, but you don't know the V1. So then you can calculate it like this. Okay. Now for flow measurement, that means the mass flow rate. For mass flow rate, it will be m dot, right? So we know the velocity, average velocity. So average velocity V2 into area will be the volume change, right? And then we have to multiply with the rho, fluid density. Then it will be the mass flow rate. Now what is coming? It is coming as A. This will be A2. So it will be A2 by root under 1 minus A2 by A1 whole square into 2 delta P rho, right? Because there is a rho here and there is a root rho here, root under rho here. So it will be root under rho only, right? Now, suppose we don't know the A2 also. What will happen? Suppose we do not know the value of A2, right? And we cannot experimentally calculate it because the system is closed, right? So this is as you can understand already that this is a closed system. So you cannot measure the A2 area, right? So what to do? So we can replace A2 with area of the throat. That is nothing but AT, which I have drawn earlier, right? Now what will happen? Now M will be, M dot mass flow rate will be ATCD divided by root under 1 minus beta to the power 4 into 2 delta P rho. And what is this CD and beta? So beta is the ratio of throat diameter by inlet diameter, and this CD is discharge coefficient. Okay, and together 1 by root under 1 minus beta to the power 4. Why it is beta to the power 4? Because earlier it was A2 by A1 square, right? So area is, so typically we know that area is the square of its diameter, right? So you can think like that, that in places of A2 by A1, now A2 is replaced with AT, so it will be AT by A1 square, and this AT by A1 is replaced by its diameter. That means it will be DT square by D1 square, right? So now if DT by D1 is beta, then it has to be squared to get the area only. Now this area has a whole square, so it will be ultimately beta to the power 4, right? So this is how your beta to the power 4 is coming. So what this term together collectively is also called velocity of approach factor. velocity of approach factor. Okay. And how this CD is coming? CD is to be calculated experimentally. Okay. Okay. Now we are talking about orifice meter next. So the example, this is common for restriction flow meter. Now particularly we are coming to orifice meter. So orifice meter is like, you get the diagram done by yourself, or you can refer any online source. I am drawing it just to understand, to make you understand. Okay, so this is your inlet, right? So from here fluid is coming. Okay, so this is the D diameter, right? And in this region there is a block. Okay, so fluid is coming here. There is a construction still in this region, and fluid is going like this. Okay, so there are two type of this vena contracta portion you can draw. Suppose the construction is in this direction, right? So fluid will be like this. Fluid will be passing like this. Okay, and there is another one when it is diverging, right? So here the fluid is like this. So vena contracta diverging out is required. Okay, so it has to be diverging out, not like this. Okay, so for this, for orifice meter, CD can vary between 0.6 to, this is 0, okay, this is 0.6 to 0.66 for orifice meter, which will be different in case of Venturi meter. This is for orifice meter. Okay. Next comes the venturimeter design. So it is little big. I'll show you the original image later. First, let me draw. Just not arrow. Yeah. So it is like this. Mm, Now there is another portion. It will be diverging out like this. Straight, it is converging, going straight, and from here it is diverging out like this. Okay. Okay. So it is bent in a certain angle. Suppose fluid is coming from here. Okay. So this bend can be of 20 to 23 degree. Okay. This angle is of 5 to 7 degree around. Okay. This is your portion 1 and this is your portion where there is a contraction. This is the portion 2, right? These two are connected manometers. Okay. From where you can take the pressure calculation. So first this portion is like this portion is converging upstream section. So in the orifice meter you can see that there is no converging portion. So it is suddenly getting constricted, right? The flow. But in case of venturimeter, it is first converging, then again it is slowly diverging. It is much more smooth, you can say. So it has a converging upstream section. This region is called the throat region, and this region is long diffuser section. So fluid is coming from here and fluid is going, and it will be creating a dead zone in both of the corners. Okay. So in this region, pressure change with respect to uh, distance is less than 0, but here del P del X is greater 0. That means pressure gradient is increasing. Okay. So what it is there? So here we are increasing slowly. That's what I just said. In case of orifice meter, there is no smoothness. It is suddenly, it is the flow area is restricted. Okay. Here in a venturimeter, we are increasing slowly the cross-sectional area so that adverse pressure drop reduces and lesser chance of flow separation. Okay. So because of this, the flow separation is higher in case of orifice meter. Pressure jump is also higher from delta P. But to reduce those things, venturimeter is designed like this. So in this case, CD, the discharge coefficient will be around 0.98 to 0.99 for venturimeter. Okay. Now suppose this venturimeter is in an angle like this. So sorry. Suppose this is an angle with respect to ground. Okay. So now we want to calculate from this is the inlet section 1, this is the constriction section 2, and from both this region there will be a manometer, right? This is very bad. Okay. So here the difference of height. So this is your delta H. Okay. And from this distance is so not it this is not anymore in the same plane. This is in Z1 and this distance is Z2. Okay. And this base height is H naught. So how the Bernoulli's equation will change here? So in this case, Bernoulli equation will contain the Z term, the static head term. P1 by rho V1 square by 2 plus GZ1 equals to P2 by rho plus V2 square by 2 plus GZ2. Right? So now P1 by rho G minus P2 by rho G plus Z1 minus Z2 equal to V2 square by 2G minus V1 square by 2G. Okay. Now we'll just rearrange this. Now if we rearrange little bit, so it will be P1 by rho G plus Z1 minus P2 by rho G plus Z2 equals to V2 square by 2G common. It will be 1 minus again V1 by V1 square by V2 square ratio. That means it will be A2 by A1 whole square, right? So this term, we can write it as H1 star. This term we can write it as H2 star. So these both are piezometric head. Okay. So it will be coming as H1 star minus H2 star equals to V2 square by 2G into 1 minus A2 by A1 whole square, right? Now from here, if we want to calculate V2, it will be 1 by root under 1 minus A2 by A1 whole square and root under 2 H1 star minus H2 star into G, right? Now from the manometer calculation, what we can get? So from manometer calculation, for the left hand side part, it is P1 plus Z1 minus H naught, right, into rho G. So for the left side, it is the pressure difference is P1 plus Z1 minus H naught into rho G equals to, in the right hand side, it is P2 plus, now you can see it is P2 and it is Z2 minus H0 and again minus delta H, right? So P2 plus Z2 minus H0 minus delta H into rho G plus delta H into manometer fluid density into G, right? Now we'll just simplify. How? We'll just expand and simplify. P1 plus Z1 rho G minus H naught rho G equals to P2 plus Z2 rho G minus H naught rho G minus delta H rho G plus delta H rho M into G. So this term and this term will cancel out. What is left? It is left with P1 by rho G plus Z1. Okay. Now if you bring back the right hand side, minus P2 by rho G plus Z2, okay, equals to delta H rho M minus rho into G by rho G, right? If you simplify, you can get it. So it will be So this H1 star minus H2 star will be, so this is again the same term, right? This is again the H1 star and H2 star, right? So it will be H1 star minus H2 star will be delta H rho m minus rho by rho. Okay, this is the expression. So if I put this value of H1 star into H2 star in the previous equation, so of V2, what will it come? So now V2 will be, 1 by root under 1 minus A2 by A1's whole square into, so it was earlier 2 H1 star minus H2 star into G. So in place of H1 star minus H2 star, we'll put this value. So it will be 2 delta H rho m minus rho into G by rho, right? So you can write V2 equals to 1 by 1 root under 1 by root under 1 minus A2 by A1 square into 2 delta P by rho, and this delta P is defined as delta H rho m into rho into G. Okay. You got the expression, right? Next comes, so it was like restriction flow parameter. Next comes the area flow parameter. I will come little later. First, let's solve for the pitot tube. It is the local velocity measurement. Yeah. So now comes the pitot tube. So pitot tube is looking like this. Okay. So there is an inlet. Okay. So this is under this case. Okay. So there is a pressure here, P. Here, stagnation pressure, PST. So it is going like this, and there is a height difference. So this difference is delta H or H. Okay. Here also there is P. This is the static pressure PS. Okay. So there are three types of pressures here. First one is the static pressure. Second one is the dynamic pressure. And third one is the stagnation pressure. Okay. So static pressure is same as the thermodynamic pressure. Is same as the thermodynamic pressure. Okay. Stagnation pressure where the fluid velocity comes to zero. So stagnation pressure corresponds to fluid decelerate to zero. That means that it completely comes to an halt. Zero velocity. Then the pressure of the fluid is called stagnant. Stagnation pressure. Okay. So now from Bernoulli's equation, there are three zones, right? So it is P by rho plus inlet velocity is there, it is V square by 2, and in the other case it is stagnation pressure by rho. And here at the stagnation pressure point there is no velocity literally, so it V is also 0, and it is in the same direction. I mean same planes, that is Z1 and Z2 will be equal. So here we can calculate the stagnation pressure. PST equals to P plus half rho V square. So this is the pressure equation in the pitot tube. So this one is your stagnation pressure. This one is the static pressure or thermodynamic pressure. And this is the dynamic pressure. Okay. So from earlier sections, we have known that P1 minus P2 is your, like delta P is your basically this expression. Delta P is this expression. So we can write it here also. PST minus P, we can write it as delta P equals to half rho V square. That means H into rho M minus rho into G equals to half rho V square. And now from here you can calculate the velocity flow inside pitot tube. It will be root under 2h rho m minus rho into G by rho. Okay. So this is the expression of pitot tube flow velocity. Next comes the area meters. Next comes the area meter. So in restriction flow meter, we have seen that m mass flow rate or velocity is proportional to root under delta P, right? Whereas in area meter, we have a linear relation between mass flow rate and measured variable. So this relation is non-linear, right? And this in restriction flow meter, but in case of area meter, this relation is linear. Okay, this is the small question may come. So now in case of rotameter is looking like this. It is very bad. So an object will be there inside the flow and we have to keep it floating mode to measure the flow parameters. Okay, so it should be straight. I am not able to draw it straight. So this total radius diameter is df. Okay, and flow is happening from the bottom, and this is little bit in angle. So this angle is a very small angle, slightly tilt. This is alpha. Okay. So it is around 2 to 3 degree. Okay. And this height, this is h height. Okay. So we'll now do the force balance. Force balance of the float. So this object is called the float. Okay. Force balance of the float. That means first it has its own gravitational weight. So it is mass of the float and its acceleration, gravitational force. Then the buoyancy force, which is coming from the fluid. So it is the area displaced by this object is mf by rho f. Okay. Then it is the not area, it is a volume replaced by this object. So it is mf by rho f. And now, so this is the fluid region which is removed. So it has to be multiplied with fluid velocity and g. Then it is the buoyancy force is equals to the drag force. Drag force is defined as, half rho af. A for means object area, projected area of the object. U square is the velocity and CD is the drag coefficient. Now if you simplify this, you will do the simplification by your own. You can just remember also, the velocity will be root under 2 mf g into 1 minus rho by rho f divided by rho af cd. Okay, so this is the velocity of the float inside this float. Now what is the volumetric flow rate? So volumetric flow rate is calculated U into area. U into area. Area means, so in the middle there is this object, right? This is the float. So area flow is happening in this region. So we have to calculate it accordingly, the area. So U into dt square minus df square into pi by 4. This is the area. Now what is dt? Right? df is the diameter of the float. And this dt is the diameter of this, basically, the upper portion. This is dt. So how are we going to calculate? dt is df plus 2 tan alpha into h. Because we have seen that it is in a small angle, around 2-3 degree, right? So we can write dt equals to df plus a into h. And a is very small. right? So now if we calculate dt square minus df square, so in the both side, if we are squaring it, it will be df square plus 2df ah plus a square h square minus df square, right? So this df square will cancel out, and as we have seen, a is very small, right? That means a square h square will be less than 2df So we can ignore this term. And after ignoring the term, we can get dt square minus df square equals to 2df into ah. Now we are putting this value in q. So q is, so expression of q is written here. So now if I put this pi by 4, dt square minus df square is 2df and there is u. U is, just now we have calculated the velocity, right? So u will be root under 2 mf g into 1 minus rho by rho f divided by rho af cd, right? Also we can write it like q equals to pi by 2 df into 2 mf into g into rho f minus rho divided by rho f into rho into af into cd, right? So this, all these terms are basically known parameters, right? We know the like defined parameters, so it will not change. Only the variation is the rho, the density. So we can write these terms as constant of k and under root rho. Why we can write, we can neglect the rho f? Because rho f is greater than rho. As rho f is greater than rho, so when it is in denominator, the term becomes very insignificant. So we are considering only the rho. So this q is almost equals to k by delta rho. Or from this, you can say, next page I am writing, that is q is proportional to h. Okay. This is the, h is the area meter. So in the earlier cases, we have seen the non-linear proportionality, but here it is the linear proportionality with the measured value. Okay. Next comes the notches and waves. So first we'll draw the rectangular notch. So it is kind of open flow channel, you have seen this is, you can imagine it as a drain, you can see, right? This is the mostly drains are in shape of rectangular open channel. So you can think of it like this. This is the open area. So this is one, this is two, this distance is h, this total distance is capital H, and this small portion is dh. Okay, and this width of the channel or notch or whatever it is b. So q is a function of this height, right? So velocity is root under 2gh, right? From Bernoulli's equation, you can calculate this, right? V equals to root under 2gh. So now, if we take the flow rate of change of flow rate change, dq will be velocity, its width, and its height. It will be dh, right? So VH we have seen at root under 2gh bdh, and it can be varied from 0 to h. So it is root under 2g is common, b root h, so it will be h to the power 3 by 2 by 3 by 2, right? So it is 2 by 3 root 2g into b h 3 by 2, right? So now, so this is q. So q is considering the discharge coefficient, it is the 2, or drag coefficient, it is 2 cd by 3 root under 2 gbh to the power 3 by 2. Okay. So now the relation is, for rectangular case, q is proportional to the height to the power 3 by 2, and change of q is proportional to the root under h, right? Next one is the triangular notch. So in the triangular notch, it is also like same. The shape now has changed. This is the open area. This is at theta angle. This is h distance. And the original height is h, and this small portion is dh. Okay. So this distance from this portion to this portion, this distance is h minus small h, right? So now if you calculate it, this total distance is 2 into h minus h into tan theta, because in the both side it is in angle, right? So you know that V equals to root under 2gh from Bernoulli's equation. Now if we want to calculate this dq again, so dq will be Vh, that is root over 2gh, into the width is now 2 into h minus h tan theta dh, right? So now if we integrate q, it will be root under 2 g tan theta, and integration should be 0 to h, and it will be capital H into small h into half minus h to the power 3 by 2 into whole into dh, right? So now if you simplify, integrate it, so it will be 2 root 2g tan theta. So it will be h 5 by 2 by 3 by 2 minus h 5 by 2 by 5 by 2. Okay, if you integrate it, simplify it, you can get this. So now if you just multiply all those things, you will get final expression as 8CD by 15 into root under 2g tan theta into h to the power 5 by 2. So now for the triangular notch, q is proportional to h to the power 5 by 2, and dq dh will be proportional to h to the power 3 by 2. So in the rectangular case, it was proportional to h to the power half. Now it is proportional to h to the power 3 by 2, right? So what we can get, that triangular notch, what we can conclude from this is that triangular notch are triangular notch has relatively higher resolution than rectangular notch. So from the expression of volumetric flow, you can understand this. Okay. So this is the basic instruments, the important instruments you need to use it. And first I will solve the equation, then I can show you some of the equipments in online. You can search it for yourself also. So first question is like, in case of closed channel flow, the flow rate depends mainly on what? In case of closed channel flow, the flow rate depends mainly on the pressure difference between the ends, right? The distance between the ends, the area and hydraulic properties of the conduit. So flow rate is governed by all of these in case of closed channel flow. Okay, so pressure difference is important. The distance between the ends are important. Area and hydraulic properties of the conduits are important. So it is all of the above. Next question. The differential pressure flow meter is based on the Bernoulli's equation, Pascal equation, Prandtl equation, or all of them. So differential pressure flow meter is completely based on the Bernoulli's equation. We have seen so far, right? Next. For laminar flow, alpha equals to 2 and true kinetic energy per unit weight can be expressed as this. So from the Bernoulli's equation, you know that it is the P1 by rho, or you can write it like P by rho plus rho g v square by 2g plus z equals to constant, right? There is alpha here. So this is the kinetic energy. This is the kinetic parameter. So alpha is 2 for laminar flow and less than 2 for turbulent flow, right? So in case of this, generally the kinetic energy term is this. right? This is the kinetic energy term. So now as alpha is 2, so it will be kinetic energy term will be 2v square by 2g. That means only v square by g. So it is option A. Next, a submarine is moving 20 meters below the surface of the water. A pitot tube containing mercury is showing the difference of the mercury level of 22 centimeters. What is the speed of the submarine? The density of the seawater is 1.030 with respect to normal water. So a pitot tube measurement. So pitot tube measurement equation we have seen, right? It is asking for the velocity. So we'll now go back to the equation we have solved earlier for pitot tube just to show. So this is the velocity of this pitot tube, right? Right? This is your pitot tube. So we'll just exactly put these values, put this equation and put the values. So V is your root under 2G delta H into rho m minus rho, basically, right? So we can also write it as, because density ratio is given, right, with respect to water. So now we'll just put the values. So it will be 2 into 9.81 into delta H is given as level difference is given as 22 centimeter, that means 0.22 meter, right? Rho m will be the mercury density 13.56 and the seawater density is 1.030. Okay. So now if you calculate, you can calculate and cross check with my answer. So it is coming as V equals to 7.35 meter per second. So which is close to this 7.54. Okay. Next, the actual velocity in the contracted section of a jet of fluid flowing from a 0.05 meter diameter orifice is 12.7 meter per second under a head of 10 meter. What is the value of coefficient of velocity? That means what is this CD? So the theoretical velocity is root under 2gh, right? So it is, head is 10. So it is 14.007 meter per second. So this is the theoretical velocity, and this is what is given is the actual velocity. Theoretical velocity or throat velocity also you can call it. So now the ratio of these two will be the value of coefficient of velocity. So coefficient of velocity will be the ratio, like V actual by V theoretical or throat. So it will be 12.7 by 14.007 is almost equals to 0.9066. 0.906. So it is option A. Next, what is the flow rate of water flowing through a 40 into 50 centimeter horizontal venturi meter when the differential gauge connected to the inlet end of the meter and its throat shows 25 centimeter mercury, assume the coefficient of discharge is 0.98. So for venturi meter, so for we'll go back to the equation of venturi meter. Yes, this is the equation of velocity, right? So first we need to calculate the head. So area is given, the density is given, CD, assume the coefficient of discharge, that is CD is 0.98. Water is there, that means water will be 1 centimeter per kg per centimeter cube, and for mercury it will be 13.6, right? Inlet diameter is given as 40. This D1 is at 40 centimeter, that is 0.4 meter, and this throat velocity or section 2 diameter is at 15 centimeter, that is 0.15 meter, right? And this differential manometer A, that is this H, delta H, is the 0.25 centimeter area, that is 0.25 meter H. So now we can calculate the pressure head from that equation. So pressure head is delta P is the pressure head is delta H into rho m minus rho water, right? So it is coming as 3.15 of meter water, right? And what was the equation here? So now we can calculate the A1, A2, right? First. So A1, A2 will be next we'll calculate the A1, A2. A1, the inlet is the pi by 4 d1 square. Pi by 4 d1 square. D1 is given as, it is same, capital D1 and small d1 doesn't matter. It is given as 0.4, so it is 0.1256 meter square. A2 will be pi by 4 d2 square. It will be 0.0176 meter square, right? Now comes the velocity part. Just a minute, one thing, let me check. So in the Venturi meter, yeah. So this is 2 delta P is delta H rho m minus rho into G, right? So we are calculating this. So in our case, in delta P, we have calculated this only. So it has to be a G. G will also be there. Or else if we don't want to calculate now, we can calculate it later also. Okay. So from the equation, if we want to put the velocity term or Q, I am directly putting it is only the V into CD. So Q equals to A to CD by root under 1 minus A2 by A1 whole square into 2 delta P. In the delta P, I have not calculated G, so that is why it will be G here, and there is a rho of water, right? So it will be, just put the values. CD is given as 0.98. So this part is coming as 0.0174 and this part is coming as delta P have calculated 3.15. This is coming as 7.8614 or 15. Now yes, so it is coming as almost 0.1368 meter cube per second, right? So in the equation, yes, so this is almost 0.137. Option A. Next, venturimeter can recover around 60% of pressure drop, 90%, 40%, none of the above. So it can recover 90% of pressure drop because of this divergent cone. Okay. The venturimeter is suitable where only small pressure heads are available. Venturimeter is suitable where only small pressure heads are available due to its high pressure recovery and high energy recovery. So venturimeter design, it ensures, so venturimeter design ensures minimal energy loss and high pressure recovery. And high pressure recovery. Okay, so this is both A and B. Next, in a lobed impeller meter, volumetric flow rate is calculated by number of revolutions per rotor. Number of revolutions per rotor. Next, an example of variable area flow meter is rotometer. Next, the relation between the angular or rotational velocities of the turbine motor or to the fluid velocities flowing through the turbine is directly proportional to each other. Okay. The different types of positive displacement flow meter are all of this. Disk meter, rotary vane meter, lobed impeller meter. So this is all of the above. Next, in rotometer, the flow rises until there is a state of dynamic equilibrium between upward differential pressure buoyancy factors with which of the following force. So it is the gravity factors. Because we have seen in the float balance, force balance of the float, we have calculated the gravitational force, differential pressure, buoyancy force, and the drag force. From where we have calculated, right? So it is the gravity factors. The flow nozzle working is similar to which of the following? So flow nozzle working is very similar to the Venturi meter without divergent cone. Option C. Next, principle of von Karman effect is employed in which flow meter? So it is all there in there are different types of flow meters are discussed in the lecture, but I have discussed the main flow meters because those are very important flow meters which we generally use in laboratory scale to calculate the different flow parameters. Okay. The von Karman effect is employed in vortex. Next, in electromagnetic flow meters, the amplitude of electromotive force is expressed as so it is defined as option A. So K E is the electric induced potential, B is the magnetic flux density, D is the inner diameter of the measuring tube, U is the average velocity. Next, Doppler and transit time flow meters are two types of which flow meter? So it is the two types of Doppler flow meter. Next, to maintain the same magnitude of temperature difference between two sensors in calorimetric flow meter, which of the flow velocity increases? So power must be increased, heating power must be increased. To maintain the same magnitude of the temperature difference between two sensors, the heating power must be increased. while the velocity increases. Calorimetric flow meter is based on the principle of temperature difference between element and medium in pipe. Option B. Thermal flow meters are operated by either introducing known amount of heat in flow stream and measuring associated temperature change, or maintaining a probe at fixed temperature while measuring the energy needed to do so. Introducing known amount of heat in flow stream and measuring associated temperature change, maintaining a probe at fixed temperature in flow stream while measuring the energy needed to do so, none of the above. So it is either introducing known amount of heat or maintaining a probe fixed. It is the option A. Which principle serves as the primary governing equation for calculating flow in differential pressure? So it is obviously the differential pressure meters like Venturi and Orphy. So it is, you know already, so it is the Bernoulli's equation. Next. In a Venturi meter, what is the purpose of the diverging cone having a smaller than the converging cone angle? So the answer is to convert kinetic energy back to pressure energy with minimum loss. So when the flow is converged, the kinetic energy becomes high, right? Because the velocity area reduces in that vena contracta region and the pressure becomes high, right? And the kinetic energy dominates at that point. So to bring back this kinetic energy to the pressure energy with minimum loss, this diverging cone is lesser. Diverging cone is done in smaller. Which flow meter is specifically recommended for measuring the flow of slurry or fluids with high levels of solid contaminants? So it is the electromagnetic flow meter. A sonic nozzle or critical flow nozzle is characterized by which of the following? It operates at Mach number 1, where flow becomes choked and unaffected by downstream pressure. Okay. In the last class, we have talked about the Mach number and compressible gas. So go through that. For a rotameter to function correctly based on the dynamic balance of forces, how must it be mounted? So it is mounted in vertical position. So some problem is there. So it is based on the Venturi meter problem or Refis meter problem. So very easy. Just do it. So water flows through a horizontal Venturi meter with an inlet diameter of 40 centimeter. That means D1 is 40 centimeter. Throat diameter is 15 centimeter. So this problem I think we have done recently, where where it is coming, a differential mercury manometer connected to the inlet and throat shows a reading of 25 centimeter Hg. The flow rate needs to be calculated. Coefficient of discharge is given. So this is done. Please go back and check. In last in last in 15 minutes back, I have only done this. So where Q is coming as approx 0.137 meter cube per second. Go and check it. Next, a submarine. So here, let me go through once again. Where was that? Yeah. So this problem I'm talking about, right? So here I have taken actually density, specific gravity. So, but here I have written specific gravity, density, so it is wrong. So it is on nothing but 1300,600 minus 1000. It is into delta H is 0.25. It is that. So it is 3150. Okay, just because I have calculated with specific gravity. So it is 3150. If we write, then you have to write it as specific gravity, but I am writing it as density, so write it as density. 3150 meter of water. Okay, so in the next case, what will happen? So this raw water is now 1000. It is not anymore 1, because 1 it is when we are taking it as specific gravity. So this 2 into, so it is coming same. Yeah. Okay, this clear? So we are doing this problem, right? A submarine moves horizontally in the sea. A pitot tube is placed in front of the submarine connected to a U-tube mercury manometer. The difference in mercury levels is 17 centimeter. Find the speed of the submarine. Okay. So it is kind of same we have done earlier, but still you can do it. So in the pitot tube problem, the flow velocity is u into root under 2 what was the expression? I am forgetting every time. Yes, 2h rho m minus rho by rho into g. It is 2h rho m minus rho into g by rho. Okay. So h is this difference, 17 centimeter, right? So 13 bar is the specific gravity. That means we have to take 13,600 minus 1000 into 0.17 into 2 into 9.81 divided by 1000. So it is coming as 6.428 almost. Okay, 6.483 meter per second. Okay. Next, a vortex flow meter is used in a pipe with a diameter The ultrasonic sensors register a vortex shading frequency, assume the Shahal number is constant, and calculate the flow velocity. Okay. So Shahal number formula is St equals to frequency into diameter by velocity, right? So now you can calculate U. Fd by St. So everything is given. 0.1 into 20 by 0.2. So it is 10 meter per second. So all these equations which I have not discussed in this class but are using is given in the lecture note. Okay, so go through that lecture note, and these are mostly the tough equations are mostly empirical equations, so you don't need to remember those things. Okay, but the basic Venturi meter equations, pitot tube equations, orifice meter equations you should remember. Okay. Next. So, in an experiment involving water flow through an orifice meter, the measured pressure drop is found to be 15 kilopascal. The pipe diameter is 30 centimeter and the orifice meter diameter is 15 centimeter. Given the coefficient of contraction is 0.625, determine the discharge flow rate of the water. So first we can calculate the area because diameters are given, right? So A1 is pi by 4 D1 square. So it is coming as 0.071 meter square. A2 is similarly 0.0176 meter square. Okay. So what is given? It is given the coefficient of contraction, but we need to calculate coefficient of discharge. So CD formula is given. It is CC by root under 1 minus A2 by A1 whole square into CC square. So put all the values and it is coming as CC is 0.625 square. Which is coming as 0.632 CD. 0.632, right? Now CD is given. We need to calculate the Q. So Q is A2CD root under 1 minus A2 by A1 whole square root under 2. So orifice meter equation was given here. Yes. To the pressure head. Okay. So it is coming as mm, you calculate independently. Okay. Then we can match. So it is coming as 0.063 meter cube per second, but answer is asked in a liter per second, right? So it is multiply with 1000, so it is 63 liter per second. This is the answer. Okay, check it. The transit time ultrasonic flow meter is installed on a pipe with a diameter D where the distance between probes L is fixed. The time for a signal to travel from upstream probe A to downstream probe B and vice versa are recorded. If the sonic velocity is c and the fluid velocity is v, derive the equation. So downstream time TAB is L by C plus V cos theta, and TBA is L by C minus V cos theta. Okay. So if we calculate the reciprocals of this, 1 by TAB minus 1 by TBA, it will be C plus V cos theta by L minus C minus V cos theta by L. So it will be 2V cos theta by L. And so now the velocity will be from the geometry. So geometry is given in the in the PDF. You just refer to that. So V is coming as L square by 2D into 2V cos theta by L equals to 2 cancel out, L cancel out. So it is L V cos theta by D. Okay. Next. So this is the sum of the derivation which is already done in the document. So I am not doing it. You just keep it for your practice. Okay. So a thermal flow meter measures mass flow by introducing a known amount of heat into a gas stream. If the upstream temperature is Tf, downstream temperature is Tw, then fluid has a specific heat Cp, then what is the mass flow rate? And the last question is about what is happening. Derive the volumetric flow rate for a rotameter based on the dynamic balance of forces on fluid. So I am giving this two as your assignment because these two are already in the lecture notes. So please go through them first and then do it yourself. Okay. So I hope from this lecture you have understood. So I have discussed mostly the basic instruments used in the lab scale for flow measurement. I have not discussed all the flow meters what has been taught in the class. So go through them and please. I have solved some of the question. I hope you will be you will face easy the this week assignment to solve these questions. Okay. So we'll meet on the next week same time. So till then, goodbye.